Mr. Kali is here for my magicians. We will continue with our precalculus course. Today's video is functions and their properties, video 2 of 3. The exercises for today says find the range of the function. The first exercise says gx is equal to 5 plus the square root of 4 minus x. The range of an even index radical starts at its starting point. Okay, so we're going to find what is the starting point. To find the starting point, we need to find the domain, where it says 4 minus x has to be greater or equal to 0. If we solve for x, we send the 4 to the other side as a subtraction. Negative x is greater or equal to negative 4. We send the negative to the other side. We change the inequality, having that negative 4 over negative 1. X has to be less or equal than 4. That means that our starting point has to start here in 4. It cannot be less. So if I substitute 4 to my function, and instead of putting gx, I put y, 5 plus 4 minus 4, it says that my range has to be 5 plus 0, because 4 minus 4 is 0, and the square root of 0 is 0. It says that y has to start in 5, and it has to finish in the positive infinite. That means that my range would be the 5 in which we start, that is our starting point, until the positive infinite. This is your answer for your range. For the next exercise, it says g to the x is equal to 3 plus x to the square over 4 minus x to the square. For this one, again, we're going to substitute, instead of, let's change our color. Instead of putting gx, we're going to put y is equal to 3 plus x squared over 4 minus x squared, the function that we had. Next step is we're going to solve for x. So we're going to send my denominator, all here that I have in the denominator, to this side to multiply the y. Y times 4 minus x squared now is equal to 3 plus x to the square. Next step is use distributive property. We will have 4y minus x to the square y is equal to 3 plus x to the square. Let's group the x to the square. I'll send this x to the square to this side, and I'll send this 4y to this side. Remember that we changed their signs. We're going to have negative x squared plus y that was already there, and this x squared that was positive moves to the other side negative, minus x to the square. We copy the 3, and this 4y that was positive moves to this side negative, minus 4y. Next step is find a common factor. They both are negatives, and they both have an x to the square shared. If we divide this number by negative x to the square, it would just be y. If we divide this number by negative x to the square, it would just be positive 1, equals 3 minus 4y. Okay, now we have to solve for x. So I send the negative to the other side, changes the sign of each side, of each number in the other side of the equation. That means that we're going to have 4y minus 3. The 4 becomes positive, the 3 becomes negative, because the negative moves to this side, dividing both numbers. Next step is move the y to plus 1 to the other side as a division. X to the square equals 4y minus 3 over y plus 1. Next thing would be send the square power to the other side as a square root. X is equal to the square root of 4y minus 3 over y plus 1. Okay, so we have our square root already. We are solved for x already. Now, what we're going to do is we're going to find the restrictions. For example, the denominator, we will continue here. The denominator cannot be 0. So this cannot be 0. If we solve for y, we send the 1 to the other side. Y cannot be negative 1. Why? Because if I substitute negative 1, it will give me a no solution answer. Once we have that, we also have that 4y minus 3 over y plus 1. Since it is inside a radical, it has to be greater or equal to 0. If we solve for y here, we send this to multiply 0 is 0. So we have that 4y minus 3 is greater or equal to 0 still, because this multiplies 0 is 0. If we solve for y, we send the 3 to the other side positive, greater or equal to 3, and the 4 to the other side negative, greater or equal to 3 over 4. Okay, so we have our two restrictions. Now, a table, okay, let's make the table. So the table would be y plus 1, that is my denominator, 4y minus 3. And then we said that from the negative infinite to negative 1 would be our first num. Then from 3/4 until a positive infinite. Okay, so these are the numbers that we're going to use. If I substitute a number that is from negative infinity to negative 1, for example, negative 2, if I substitute negative 2 here in y, my answer is going to be negative. If I substitute negative 2 here in y, the answer is again negative. Negative times negative is positive. The next one, from negative 1 to 3/4, I can substitute a number that is between them. It would be 0. An example, if I substitute 0 here, the answer is positive. And if I substitute 0 here, the answer is negative. Positive times negative is negative. If I substitute a number that is greater than 3/4, for example, 3, if I substitute 3 here, 3 plus 1 is 4, is positive. If I substitute 3 here, it would be 12 minus 3 is also positive. Positive times positive is positive. That means that your range has to be somewhere between here and here. In other words, your range starts from the negative infinite, comma, until the negative 1. The negative 1, remember that you cannot use it, so we close it in parentheses, both. Union, we don't use any number here because the answer was negative, so we don't use any number between these two numbers. We put the 3/4, but the 3/4 is inside brackets because 3/4 can be, look, it has an equal sign. So 3/4, comma, until where you finish, that would be the positive infinite. Infinites are always in parentheses. And that would be the answer for this exercise. That will be your range for both exercises. Let's continue. The next explains continuity. Okay, so he says, for the first one, that is this one here, he says, this graph is continuous everywhere. Notice that the graph has no breaks. It continues, it is a pure graph, it has no breaks. Then we have the one that says removable discontinuity. This graph is continuous everywhere except in this hole here. Okay, at x equals a. This is called the removable discontinuity because it can be patched by redefining the function. Okay, it can be patched by redefining the function. Then we go for the removable discontinuity also. It says this graph is also a removable discontinuity at x equals a. Okay, at x equals a. Then we have the jump discontinuity. Here is a discontinuity that is not removable. It is a jump discontinuity because there is more than just a hole at x equals a. There is a jump in the function, the values that make the gap impossible to plug with a single point. And the last one says that this is a function with an infinite discontinuity at x equals a. This one is definitely removable. Okay, this one has to be removed. Okay, now we're going to continue with the next type of exercise. It says, graph the function and tell whether or not it has a point of discontinuity at x equals 0. If there is a discontinuity, tell whether it's removable or non-removable. Okay, so the first exercise says g to the x is equal to 3/x. The first thing that I'm going to do is that I'm going to find my restriction. X cannot be equal to 0 because it will be an undefined answer. That means that in my table of values, that is easy to make our graph with a table of values. We're going to use any number we want to except 0. I will use numbers that give me whole numbers as answers. Okay, so I'll use -3, -1, 1, and 3. If I substitute -3 in x, my answer is -1. If I substitute -1 in x, my answer is -3. If I substitute 1 in x, the answer would be 3. And if I substitute 3 in x, the answer would be 1. Once we have these points, we're going to make our graph. Okay, so it says -3 with -1, it's here. Then we have -1 with a -3 is here. Your graph looks like this. For the next one, we have 1 with 3 would be here. And we have 3 with 1 would be here. Your graph looks this way. Okay, so we have our graph. As you can see, the graph, yes, is discontinuous. So it has a discontinuity, and the graph, it looks like the one that we said here, that is an infinite discontinuity. That means that it's removable, non-removable. Non-removable. Okay, next exercise. The same thing that we did in this exercise, we're going to find the restriction, and the restriction is actually the same. X cannot be 0. That means that in our table of values, we're going to exclude that 0. We're going to use the same numbers we used in the last exercise. If we substitute -2 in every x that we have here, -2 to the cubic power plus -2 over -2, the answer would be 5. If we substitute -1 in every x, the answer would be 2. If we substitute 1 in every x, 1 to the cube plus 1 over 1, the answer again is 2. And if we substitute 2 in every x, the answer would be 5. Once we have this, we're going to make our graph. It says -2 with positive 5. 1, 2, 3, 4, 5. It would be around here. -1 with positive 2 is here. Then we jump because we cannot use the 0. 1 with 2 and 2 with 5. As you can see, your graph looks like this. Okay, your graph looks like this. Yes, it's discontinuous and it's removable. Okay, how do we know that it's removable? It's like if you remove this part of the graph just to continue in the other side. Okay, with that, we're going to continue with the next type of exercise. He says, graph the function and identify the intervals on which the function is increasing, decreasing, or constant. Okay, so we need to find if it's increasing, decreasing, or constant once we have our graph. For this type of graph, I really recommend, since the domain is all real numbers here, you can substitute any number and it will also always give you an answer. I recommend use numbers that start with -2 and then use numbers that are going to the positive side until you see your graph that is finished. So we're going to start using -2, -1, 0, 1, 2, and we will see what the behavior it has. If I substitute -2 in this x and I plug everything inside my calculator, the answer would be -6. If I substitute -1, the answer would be -1. If I substitute 0, the answer would be 2. If I substitute 1, the answer would be 3. And if I substitute 2, the answer would be 2. Let's make our graph to check the behavior. Okay, so if we substitute these numbers, we have -2 with -6. 1, 2, 3, 4, 5, 6. It would be around here. Then we have -1 with -1. It's around here. 0 with 2. Then we have 1 with 3. Then 2 with 2. Okay, so I'm going to need more numbers. As you can see, your graph doesn't seem complete. So let's use 3 and let's use 4 to check. Okay, if I substitute 3 here, it will be 3 minus 1 to the square, and then 3 minus that answer would be -1. If I use 4, it will give me 6 negative. Okay, so if we use these two numbers, it says that 3 with -1 and 4 with 6. As you can see, your graph has a curve this way. Okay, your graph has a curve this way. Now, we have to identify where it is increasing and decreasing. So it's increasing. We can say that it increasing or it increases. Okay, it increases here. From here, you read from left to right. It increases from the negative infinite, that means the arrow, until this number here that you get. So it will be until 1, right, in x. So we're going to say that it increases from negative infinite until 1. Okay, 1, we can use it because the domain is all real numbers. Then, from 1, it starts decreasing. So we can say that it starts decreasing from 1 until you get to the positive infinite. Until you get to the positive infinite. And that would be your answer. Thank you for watching. Don't forget, math is magic.